Hello everybody. In this video, we are going to solve this problem that is given the function sin z by z cube where z is a complex variable. Then at point z equal to 0, what is it? So is it a pole of order 3 or a pole of order 2 of order 1 or is it not a singularity? So stay tuned till the end of this video because at the end, I shall also discuss about the practical functionality of this particular problem. So at the very first glance, students might tend to commit a silly mistake. That is, the moment they observe z cube in the denominator, they will think that at z equal to 0, the function tends to infinity. So z equal to 0 is a pole of order 3. But this is incorrect. Now let us try to understand the question itself. So the examiner here is asking that what is happening at z equal to 0 because there might be something suspicious. So it is possible that the denominator is becoming 0 and that is the reason why the entire function tends to infinity. So that means there is a possible pole. So now what is a pole? So a pole is a point where the function becomes infinity. So if you are given a function f of z is this, then we can say that z is equal to a is a pole of order n. So example, if f of z is 1 by z, then z equal to 0 is a pole of order 1. Likewise, if f of z is given this expression, then z equal to 3 is a pole of order 5. So remember, z equal to a, this identity is a pole. Z is not a pole, a is not a pole. But the identity z equal to a, that is a pole of order n. So now coming to the thought process to solve this question. So given that f of z is the expression where numerator is sin z and denominator is z cube. So at that point, at what point denominator becomes 0? So that is obviously equal to 0. So at z equal to 0, does numerator also become 0? So that is sin z is equal to sin 0 is equal to 0. So yes, it does become 0. So we have 0 by 0 form at z equal to 0. So it means there could be some terms in numerator and denominator that are common and can be cancelled out. So now let's look into the step-by-step solution. So since we mentioned that there are some terms in numerator and denominator that are common, so it means that sin z should be expressed in terms of power. And that can be only be done by Taylor series expansion. So sin of z can be expressed in this format. So you can cancel out the common terms and this is the final expression that you get. So here if you observe that z square is the only term which is a denominator. So for this function at z equal to 0, f of z is infinity. So therefore, at z equal to 0 is a pole of order 2. So coming to the shortcut method for gate, so near 0, sin z approximately tends to z itself. So f of z can be expressed in this particular fashion. So you have 1 by z square. So z equal to 0 is a pole of order 2. Now coming to the practical examples for this. So consider a simple spring mass system given by this expression. So taking the Laplace transform, you land up into this expression. So the transfer function is response upon the force. That is, you get this particular expression. So to get the poles of the system, you need to equate denominator to 0 and that is what you land up at. So these poles determine the natural frequency, the oscillation behavior and the stability. Now coming to the last point, that is resonance in structures. So when the excitation frequency reaches the system's pole frequency, so the amplitude becomes very, very large and that causes resonance. This is why turbines, bridges and rotating shafts must avoid operating at resonant frequencies. One of the classic examples of such failure is you can observe the Tacoma Narrows Bridge way back in 1940 that involved the resonance behavior.